Okay. We will be considering now the computation of DFT. So, we will be basically discussing today first Fourier transform, FFT. So, FFT is a big topic and there are many algorithms under FFT. We will consider the basic one, which was developed by Cooley and Tukey long back in early 70s when they were working at IBM. FFT. Now, before that, suppose we are considering, we see the formula of DFT. Xk is okay. Now, this you have to calculate for k equal to 0, 1 up to again n minus 1. So, k also has the same range, but for each k in this range you have to carry out this sum to get the corresponding xk. In this summation you have a product xn into this. So, typically xn could be complex and this is complex, or xn could be real. So, let us assume xn to be complex in general. You have got one complex number, another complex number, z1 into z2. Suppose you call it z1, it is z2. You have a product of two complex numbers, and how many such products? N equal to 0, one case, n equal to 1, another case, n equal to up to n minus 1, another case. So, total n. So, that means you need n number of complex multiplications. And then you are adding them. How many additions? I mean, if you are having total n number of terms and you are adding them, basically you need n minus 1 complex additions. Okay. Now, one complex multiplication in general will be of the form a plus jb, c plus jd. If you multiply, you have ac minus bd plus j ad plus bc. So, one multiplier AC, one BD, two multiplier, and then AD one multiplier, BC one multiplier. So, you need four multipliers, four real multipliers. Two are used for the real part, two are used for the imaginary part. In fact, so totally you need four multipliers, but by some tricks which I am not showing here, you can bring down from 4 to 3, okay, by introducing some additional terms. So, addition will go up, okay, but whatever, this is complex multiplication. So, complex multiplication can have 4 or sometimes 3 real multipliers, because all your multipliers in hardware will be real multiplier. You will be putting them in some way, in some format, okay, and then considering something to be complex and all that, but all multiplications in real hardware will be real multipliers using real digital hardware. So, and multipliers take much more complexity than additions. That is why in our computational analysis we will be bothered only by multiplications. That is, our goal will be to bring down the number of multiplications. Okay. By that process, addition also will go down, but we are not so bothered about additions, because additions do not take much hardware. Multipliers are very hardware hungry, they take much more, they have much more complexity, they take much more hardware. So, 16-bit into 16-bit multiplier. So, you have got to add, I mean, you have got so many rows, shift add, shift add, shift add, and the whole thing will take a 16 by 16 array. It will be, it will be consuming a lot of hardware. We will have more complexity, or in terms of time, if you want to do, it will take more time. So, that is why multiplications are, or multipliers are of interest to us. Our purpose will be to bring down this computation, because suppose n is large, suppose n is 1024, then per output, per k, you need 1024 multiplications, complex multiplication, and each complex multiplication can itself have 4 or sometimes 3 real multiplications. So, that many real multiplications for each k. And again, k will have how many cases? Capital N cases. So, n cases each with n complex multiplications. So, you will have n square complex multiplications. You understand? If capital N is 1024, it will be 1024 square to compute all the x case. That will be too much of computation. That is why, when DFT came, one main goal was, by all the researchers, one main goal was to bring down the computational complexity, and that led to, by exploiting the inherent mathematical structure, symmetry, and many other properties. Okay. And by that process, many fast algorithms came up. One basic algorithm, which is Cooley-Tukey's algorithm, called decimation in time. This algorithm will be considering today. So, we have got n square complex multiplications and n into n minus 1 complex additions. Per k, I have got n minus 1 complex addition. So, n into n number of values for k 0, 1 up to capital N minus 1. So, total n possibilities of k. So, n into n minus 1 complex additions, and we will be modifying the algorithm, so that this goes down, this computational complexity goes down significantly. But for that, first we will assume n to be a power of 2, maybe 2 to the power r, that is n can be 64, 128, 256, 60, 32, okay, 16, like that. Now, you can ask me, suppose n is 14, then what to do? Then we will simply append 2 zeros to make the length 16. Okay. So, we will append necessary zeros to make the length a power nearest power of 2, okay, nearest power of 2. So, 2 to the power r, or sometimes we can also write log of n to the base 2 is r. This is one thing we assume, and so the algorithm I present will be valid for this, but then there are many modifications of the algorithms where n can be any arbitrary number, it may not have to be a power of 2, and there are still sophisticated algorithms available. Okay, but for our purpose we will take n to the power of 2, like this. Another property, this is x k, k is from 0, 1 up to n minus 1. Suppose k, we jump from k in this range by another small m, where small m is again between n minus 1 to 0. That means, we already had a range 0, 1 dot 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 up to n minus 1, k could be somewhere here k, and from here we are jumping by m. So, it is k plus m, and m can be, if m is 0, m can be 0. Okay. So, you are having k, then k plus 1, k plus 2, then you cross to this side. Maximally it can be up to here, to n minus 1, this is n to n minus 1, because if k is at n minus 1 and then small m 0, then minus 1, small m 1 n, small m 2 n plus 1, small m 3 n plus 2, like that. So, finally, you can go up to this. Okay. So, if I take k and suppose m, I do not take arbitrary m, I take n. Now, I am taking a specific n. So, it will be k plus n, it will be in this block, in the same place, from 0 to n minus 1, anywhere you start and then jump by n. What will be, if I replace k by this thing, k plus capital N in this summation, in the right hand side summation, what will that be? That will be that summation and if you take that capital N out, 2 pi capital N by capital N, that is 2 pi into small n, e to the power minus j 2 pi into an integer small n, that is 1. So, you will get back original summation. Okay. Which is your original x k. That means, if I extend this formula and take k beyond that range, so x k plus n will be same as x k. K is within this range. If you go from any k within this range by plus n, you will get the same thing. And why plus capital N? By the same logic, k plus 2 n, k plus 3 n, k plus 4 n, k minus 2 n. So, that means, x k periodic in k over n, where x k is an n point, remember n point DFT. That is, the original length of the sequence was capital N, x small n was length capital N, I took its n point DFT, that n was coming here, and small k also will be over the same range 0 to m minus 1. That n point DFT is periodic over k over a period, periodic in k over a period capital N. These two facts I will use. Then what I will do? I will divide the sequence into 2 hop, that is, say x 0, x 2, x 4 dot 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 dot. Now, n is even, because n is 2 to the power r. So, this is n minus 1 is odd. So, I can, if I am hitting the even points 0, 2, 4 dot dot dot, then I will go up to n minus 1. So, these are the points I target. So, how many of them are there? Half. N is exactly even, so half, and n was 2 to the power r. So, now we will have n by 2 points, that means 2 to the power or minus 1 points. And so, that I take those points out, form one set, okay, and I take x 1, x 3, x 5 dot 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 dot, these are like the polyphase factors. Okay. You are basically you are doing polyphase decomposition by 2. 0th polyphase component is x 0, x 2, x 4 dot dot dot, and first polyphase component is x 1, x 3, x 5. Just that. Okay. Since in those good old days of FFT, polyphase decomposition did not come up, so they write like even part and odd part. But now you know polyphase decomposition. If I have this sequence x 0, x 2, x 4 dot 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 up to x n minus 2. Okay, this is 0th polyphase component. And how do you get it? If you just decimate by 2, you get it. And another component is x 1, x 3, x 5 dot 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 x n minus 1. Both have how many? This is first. Okay. Both have how many terms? N by 2 here, n by 2 here. There is 2 to the power r minus 1 here, 2 to the power r minus 1 here. This sequence we normally call P 0 n, okay, polyphase component, and this is P 1 n, but instead I will just use another notation, maybe H n, this is G n. Okay. So, H n is a n by 2 point sequence. Therefore, if I have to consider is DFT, it will be n by 2 point DFT. If I have to consider DFT, it will be n by 2 point DFT. If I do not have additional zeros and all that, which I am not appending, n by 2 point DFT. Okay. And H n, let it have H k and G n G k. Both are n by 2 point. That is, k here will be 0, 1 dot 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 n by 2 minus 1, because length sequence, each sequence is of length n by 2. So, total number of point n by 2, if you start from 0 and 1, you have to go for n by 2 minus 1. That is H n, it will have capital H k, G n, capital G k. Both are n by 2 point DFTs, n by 2 point DFTs. Fine. Now, let us come to the original DFT. Original DFT is okay. Now, here I will take the even part out, those terms I will write in one place, that is x, n will be 2 r. So, r can be 0, r can be 1, that is 2 into 1, okay. R can be 2, 2 into 2, like that. R here is how much? N is a power of 2, so n by 2 minus 1. So, r 0, that is x 2 into 0, that is 0, x 0. Then r 1, that is x of 2 into 1, x 2, this term. R 2 means x of 2 into 2, 4, this term. So, those terms, and how many r's? Total terms is n by 2. So, 0 to it will be go up to n by 2 minus 1. And so, those terms I write separately, and another one also will be here, that I am coming to. X 2 r e to the power minus j 2 pi k. So, n is replaced by 2 r. So, this is 2 r by n, because n is taking either 0 or 2 or 4 or 6 or 8 like values. So, if I write n as 2 r and r will be 0, 1, r is 0, 1, 2, all those 0, 1, 2, 3 fully up to n by 2 minus 1. So, here small n becomes 2 r, here also small n becomes 2 r. Okay. So, that is one part, one half of the summation. Another half of the summation also will be here odd terms, x 1, x 3, x 5. So, this you can write as x 2 r plus 1. If r is again 0, if r is 0, it will be x 1. If r is 1, x 3. If r is 2, x 5 dot dot dot. And total how many? Again total number of terms here is n by 2. So, if you start from 0, it can go only up to n by 2 minus 1. And small n is this, so to the power minus j 2 pi k by n, and small n will be 2r plus 1. All right. Now, what is x 2r? X 2r is hr. What is hn? Hn is x 2n. Okay, this is a 0th fellow. This is the first fellow, h1, h2, h2 is x 4. So, hr is x 2r. Okay, h0 x 0, h1 x 2 into 1, h2 x 2 into 2, 4, hr x 2r. So, this is nothing but hr. It is nothing but just renaming those x samples by h samples. X 0 is h 0, x 2 is h 1, x 4 is h 2. So, that way it is hr, x 2r is hr, and this I can write this way, e to the power minus j 2 pi k r by n by 2, n by 2. Now, n is power of 2 to the power r. So, 2 to the power is divisible by 2, n by 2 also is an integer. So, like this, and here h x 2r plus 1. What is x 2r plus 1? If r is 0, x 1, that is g 0, g 0 is x 1, then g 1 is x 3, g r, this is rth, 0th x 1, g 0 is x 1, g 1 is x 3, that is 2 into 1 plus 1, g 2 is g x 5, that is 2 into 2 plus 1, g r 2 into r plus 1, that is x 2 r plus 1 is g r. From here you take out e to the power minus j 2 pi k into 1 by n, that separate, and that does not depend on r. So, that I can write outside. Okay. And here e to the power minus j 2 pi k 2 r by n, again I write as r by the same manner n by 2. Okay. Now, remember I am finding out this DFT of original sequence. So, k range was 0 1 dot 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 n by 2 minus 1, then n by 2, then n by 2 plus 1 dot 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 up to n minus 1. Basically 0 1 up to n minus 1, I have written these intermediate points. Okay, because original sequence has that much of length, capital N. So, k also will go from 0 to capital N minus 1, because small n was from 0 to capital N minus 1. But this I am writing in this way, and I am taking the upper half, or maybe you can say the lower half, up to this 0 to n by 2 minus 1, that is one half, and that is another half. 0 1 up to n by 2 minus 1, one half, and then n by 2 plus 1, n by 2 plus 3 dot 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 up to n minus 1, that is another half. Both halves have how many terms? N by 2 terms. Now, suppose, so k is varying over this entire range from 0 to n minus 1. So, I will have k equal to 0, run this summation, find out k equal to 1, do this, again find out x 1 dot dot dot. Suppose for the time being I am finding out x k for this upper half, k equal to 0 1 only up to n by 2 minus 1. The remaining part, sorry, the lower half, the upper half part I will do later. So, if k takes these values, so look at this summation now. Summation hr, hr is a sequence, how many points? N by 2 points, h 0 that is x 0, h 1 that is x 2, h 2 that is x 4, h 3 that is x 5, h 0 that is x 0, h 1 x 2, h 2 x 4 dot dot dot, hr x 2 r, okay, like that. So, this is hr sequence e to the power minus j 2 pi k into r, and k also is taken to be with the same range as that of r. So, h was a finite length sequence of length n by 2, h 0, h 1, h r, that is x 2 r up to h n by 2 minus 1, which is this. For that sequence, if I carry out its DFT, n by 2 point DFT, this one, okay. What will that be? That h k is nothing but this summation, where k will be over this half only, the same range 0, 1, 2 up to n by 2 minus 1, and that is what I am finding out, because I am taking k for the time being only over this lower half. So, this will be nothing but h k, that is for this sequence, if I take its n by 2 point DFT, k will be over this range only, because r is over this range, time index r is over this range. So, k also with the same range. So, this summation will be h k. Similarly, this summation g r, so g r is a sequence g 0, g 1, g 2 dot dot dot. Okay. So, g r is a sequence, and what is the length? What is the range? R from 0 to n by 2 minus 1. What is the range of k? Same range, and instead of n I have n by 2 here, n by 2. So, it is basically, if you want to carry out g k, this will be g k, because length of this time sequence g r is n by 2. That is why it is n by 2 coming. E to the power minus j 2 pi k into r, r is the summation index, time index, but k should vary over this part only, 0 to 0 1 up to n by 2 minus 1, because r, that is the time index, also varies over this range only. K also has the same range, must be having the same range, and that is done. So, that means for that k, this will be g k. So, h k plus e to the power minus j 2 pi k by n into g k. Okay. Up to this, if we see, are we gaining anything? Say for k equal to 0, you carry out this summation. For k equal to 1, you carry out this summation. Every time, how many multiplications? N by 2, because the summation has n by 2 terms, 0, 1, 2. Every time you multiply each one complex value with another complex value. And now, total how many? N by 2 for each k, and here again for each k n by 2. So, n by 2 times n by 2, okay, for this half of the k, and again n by 2 times n by 2. So, twice this, and plus this term into this, okay, this term into this means for k equal to 0, 1 multiplication, for k equal to 1, 1 multiplication. How many k? N by 2 k. So, another n by 2. So, n square by 2 plus n by 2. All right, n square by 2 plus n by 2. Originally, I had n square. Okay, originally, I had n square complex multiplication, right. Now, it is appearing to be, so that is for the lower half of the k, but I want to find out the same thing for upper half of k. So, if you go for upper half of k, that is k equal to, you put this n by 2 or n by 2 plus 1 dot 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 n minus 1. So, apparently, for that half also, if you carry out, if you put the various values of k from that upper half, again same thing you have to do. I mean, the summation for every k you choose, there will be one complex number times another complex number. Each I am taking to be general, in general complex. If it is real, it is real. So, I am considering general case. So, complex into complex, complex into complex, complex, again another n by 2, because upper half also has length n by 2, and for each k there in this summation again n by 2 terms. Okay. So, n by 2 into n by 2, same thing, okay, plus n by 2 into n by 2, the same thing, you know, and this also will give rise to another n by 2. So, twice this. Okay. So, it will give rise to n square plus n. So, we are not getting anything, because if you forget about this n is say very large. So, n square is much larger than n, it is n square, originally n square. So, what the hell have I got out of this, you know, by this breaking and all that, have I got anything? Answer is yes. What? When k goes out of this range, k, h k is periodic in k, but over how much? For the range of k is n by 2. So, h k is periodic over n by 2, that means h k plus n by 2 is same as h k. Similarly, g k plus n by 2 is g k. So, the moment I go from the lower half to upper half, what is n by 2? N by 2 is 0 plus n by 2. What is n by 2 plus 1? It is 1 plus n by 2 plus 1. What is n by 2 plus 2? It is 2 plus n by 2. What is n by 2 plus k? It is k plus n by 2 plus k. So, if you have to find out h at these values, n by 2 plus k, I do not have to do any calculation, because I can just go back by n by 2, whatever value I got earlier for h k, I can simply substitute that. So, I do not have to do any calculation. Okay. So, for the upper half, this does not require any calculation. For the upper half, this does not require any calculation. Only thing is this multiplication, this I have to carry out, because here it is capital N. So, if it is periodic over k equal to 0 to n minus 1, that is for a period of k equal to capital N, okay, not over n by 2. So, k equal to 0 1 value, k equal to 1 value, you will go up to k equal to n minus 1, you get different values, then only it will repeat. Okay. So, that means when I go for lower half, I had this many terms coming from this. When I go to upper half, again another this n by 2. So, n square by 2 plus n by 2 plus n by 2. So, it will be n square by 2 plus n. Originally, I had n square. So, n square is becoming n square by 2 just plus n. So, it is coming down by factor of 2. If n is large, forget about n as compared to n square by 2, n square. So, from n square, originally I am getting n square by 2. Okay. And one more thing, this term e to the power minus j 2 pi k by n. You are multiplying something, right? This into g k. Suppose you had a k from this range 0 1 dot n by 2 minus 1. Suppose here is k. So, you find out this product, and then k goes up to k plus n by 2 in the upper half. This was the lower half, upper half. Okay. For k plus n by 2, it will be e to the power minus j 2 pi k plus n by 2 by n into g k plus n by 2, but k is periodic over n by 2, because g k is an n by 2 point DFT. So, g k plus n by 2, as I told earlier, g k plus n by 2 is same as g k, okay, because g k is periodic over n by 2. So, g from any k, if you jump by n by 2, you get the same thing. What happens to this quantity? When I jump, k jumps from the lower half to upper half. If you take out this n by 2 terms out, it is power minus j 2 pi into n by 2 by n. So, n cancels, 2 cancels, you have got e to the power minus j pi, okay, into the same thing, 2 pi k by n into g k. Okay. Originally, I had this, k has jumped now, k has jumped by n by 2. So, instead of k, I had k plus n by 2, instead of k plus n by 2, g k plus n by 2 is g k, and this is this. Okay. So, I replace g k, and this part is out, but what is e to the power minus j pi? That is minus 1. So, it is minus of what I had earlier. So, you see, when I k moves to the upper half, even this product I do not have to calculate again. Whatever the product was, this product g k into this was, if k jumps from k to k plus n by 2, the same thing will prevail, only sign will undergo a change from plus to the minus. So, it will not require any multiplication, it will only be minus. So, what kind of structure it gives rise to and all, I will do in the next section. Thank you.